So I realize I'm standing between you and a barbecue, so I will try to make this short and sweet. Okay. So I have nothing to disclose, but I do want to mention that I am a unbiased user of virtual photonics tools in both space, time, and frequency. So take that for what it's worth. Okay, so what is it that we're going to hope to accomplish here this morning? So there's three main things that I would like you to walk away with by the end of the morning. First one is about the control of the optical path length. You can control that path length in multiple ways. You saw examples of this in Bruce's clinical talk. I'm going to show you more mathematically how that works. You control the path length by controlling the wavelength, the spatial extent, and the time or frequency content. Controlling the path length or measuring the path length is what enables you to measure optical properties. In this particular case, I'm going to be referring to the absorption coefficient and the reduced scattering coefficient. The measurements we're talking about, like Bruce discussed, are macroscopic, large volumes of tissues, very difficult to separate this anisotropic scattering, mu s prime, from the actual scattering path length. That's more of a microscopic measurement. I usually don't do that. It's not in my contract. And then finally, the goal, well, anyway, then the goal is, of course, why do we do this? Why do we measure absorption and scattering? It's enabling us to measure or to quantify molecular absorbers, hemoglobin, water, lipids, concentrations, and states. And you saw why that's relevant, but now we'll get a little bit under the hood to show you how that works. So, as if I have to explain why modeling is important, but I think it's critically important that you know, as scientists in the field, why we spend all this time modeling photon light propagation and whatnot. And one example that I'll bring up is something you saw before. This was one of our largest projects where we use these diffuse optical spectroscopic tools. They measure hemoglobin, water, and lipids below the surface in tumors. And the idea, and I think you might have seen the same slide, is that we can see that tumors generate optical contrast. They change the hemoglobin, more hemoglobin. They typically have more water through swelling, edema, and they typically have fewer lipids, at least in the breast. And you can see that these spectra are different. And then as these tumors are treated, you can see how the malignant tissue spectrum begins to approach more the normal tissue spectrum. This is fantastic and wonderful, but what if that's just a fluke? What if it's the way someone held the probe? What if it's something the person ate that day for lunch, which can affect your optical signals, by the way? How do you know that these changes are really confined to the tumor region and are not some global change or instrumentation? Well, modeling is one way that you can discriminate those types of changes. In other words, our clinical trial we just did is basically random. We don't want that. Another example is found in the brain. This is through published work that we have done, where what we're doing is we're putting these diffuse optical sensors on the brain during routine surgeries. And what we did here in this particular case was measure the oxygenation of the brain using frequency domain techniques during these routine surgeries. And we saw, for example, that different drugs, different types of pressor drugs, these drugs are used to increase your blood pressure, which tends to happen if you lose blood during surgery, fairly routine. The drugs work great, but one curious finding was that some of these drugs would actually desaturate your brain. Makes me not want to ever go to surgery, whereas other drugs did not. Is that a real effect? Is it an artifact? How do you know? Well, one thing that's very interesting is that a recent paper just showed with a CW method, there was really no model development in this discussion, they showed that these changes are over 20%. If your brain desaturated 20%, you would be in serious trouble. Whereas you can see here, these changes are only several percent. Which one's right? How do you know? It turns out they found out that most of that change was due to the skin blood flow changes, not in the brain. You can see why modeling is important, because we're fairly sure that this is happening in the brain, not in the skin. And finally, one other example on a much grander scale, there's been a big push in the cerebral oximetry market to look at what happens in the brain, especially during surgery. And there was this fantastic study published a few years ago that looked at, during surgery, if your brain saturation, hemoglobin saturation drops too low, you can see that, and the magic number that they picked was 50%. If it dropped below that value, I believe Bruce used this example in the previous, just to make sure I wasn't speaking in Greek, which I can't do, except for symbols in math. But anyway, what happened is that if your brain saturation maintained above 50%, your survival long-term later was much higher than for those whose brain saturations dropped below 50%. A startling finding if ever there was one. Question, Is 50% really the magic number? What if it's 51.7%? What if this is a fluke? What if the real number is 72%? How do you know? The system they used is not very good at narrowing down absolute values of oxygen saturation in the brain. Could we discover better separation if we had better measurements in the brain? Well, that's what we're trying to research. So modeling helps us uncover the true origins of biochemical signals. And I like to think of modeling as the Rosetta Stone of biomedical optics. If you're not familiar with the Rosetta Stone, the idea was that this was a stone that was found, I believe, by one of the Napoleon soldiers that had the same text in multiple languages and allowed them to translate ancient languages in terms of modern linguistics. Well, biophotonical modeling is the same thing. It allows us to translate optical measurements, whether in space-time or frequency and wavelength, and allows you to uncover biophysical structure and function. And that's critically important. Okay, so hopefully if you're not motivated after 5 days of hearing this, I don't know that that did it, but anyway. So what exactly is our goal? So within the confines of absorption spectroscopy, which is mainly what I will talk about here this morning, you're definitely, I'm sure, familiar with something called the Beer-Lambert law. The Beer-Lambert law tells you how the intensity of light moving through a sample, in this case a laser beam with a copper sulfate dye, that the attenuation in this signal is related to three major components. One of them is the molar extinction coefficient. That's essentially the darkness of the molecule. A high extinction coefficient means it absorbs very strongly at that wavelength. The concentration, if you add more of it, you're going to get more collisions through the sample, less light coming out the other side. And this mischievous little thing called S, sometimes called L, otherwise known as the optical path length. In the spectrophotometer, this photon path length is the dimensions of your sample. In tissue, this is nowhere near true. In tissue, in this case, I've just added some milk to the sample. The photon path length is now, as you have seen with mathematical rigor, you've seen that this is a very serpentine, diffusive path length, goes in all directions. Notice how the spot going through the sample has now disappeared as there is light emanating from all over the sample. How can you correlate now these changes in intensity to absorption? You can't if you don't know the path length. If you know the path length, then you know how much of the intensity at decay is actually due to absorption, to extinction, as opposed to also scattering. And since as I believe Bruce showed you, in the near infrared, light transport is mainly scatter dominated. So you're losing you're missing a lot of information by not measuring scattering. And I'll give you a clinical example of this. You need to know and control the photon path length. Here's a study, for example, that we did in little babies. They're so cute. And we wanted to figure out, since I have 5 myself, I love kids, we actually measured something called the differential path length that's inside of the kids. And this is a mathematical expression that relates the source detector separation to the photon path length. And you can see this differential path length is a function of the scattering, the absorption, and the source detector separation itself. Well, what we did was we measured in about 21 different kids at 4 different wavelengths. You can see the variance in this differential path length. Each dot represents a different kid. Each dot represents a different soul. And you can see this huge range of values. How do you know which one is right? You can take statistical guesses and say, yeah, that's the average, but not everyone is the same. People are not the same. How do you know? Well, it's going to affect your clinical diagnosis unless you know exactly what that path length is. If you know what it is, or you measure it, or it's well determined or confined, that allows you to access this information due to absorption much more accurately. One more example, this one from the virtual world. In this particular example, we are very interested in looking at, for example, how blood vessels respond to different types of stressors. And what we did was, since we're measuring this in the clinic, we decided to do some modeling to figure out what's going on. I just wanted to show you this. This is an example of a simulated occlusion where, let's say you put a near-infrared sensor on a wrist or a finger or something, and you do an arterial occlusion. You're stopping blood flow into that region of tissue. And I made up an occlusion response. The oxyhemoglobin dropping during the occlusion, bottoming out, you release the cuff, you get a big overshoot due to the vascular elasticity of the blood vessels, and then ideally it would recover back to its baseline value. This is a highly mathematical construction. Real people do slightly different things. The deoxyhemoglobin, notice it kind of does the opposite. levels off and returns to baseline. So this is some kind of idealized occlusion response. But what we did was we calculated the reflectance of one of our probes using two different scattering spectra. One of them having a realistic tissue scattering shape, the other one having one that's more flat. One could be more like muscle, the other one could be more like lipids. And you can see that if you use what is probably the predominant method for calculating how to look at changes in hemoglobin, which is essentially just looking at a couple of wavelengths and doing differentials and all this stuff, you can see that none of these curves look like those curves at all. They look completely different. Not only that, I don't know how well visible it is, but you will see, maybe bad choice of color on my part, not only do you not faithfully represent the true hemodynamics, but you will see that you get different answers depending upon what scattering I put into the model. Once again, if you don't know the scattering, even the relative changes in the signal are going to be compromised. And there's a lot of talk that, yes, you can count, you really can't. Unless you know the scattering or measure it, you're always going to measure even relative quantities inaccurately. And now you know why we spend so much time modeling and coming up with technologies that measure the true photon path length to avoid problems like this. Okay, so going back, the key is controlling the photon path length. And you saw examples previously of how you can control the path length by looking at different wavelengths. In this particular case, you can see that in the visible at 400 nanometers, your penetration is significantly compromised in the tissue. Whereas in the near-infrared, 850 nanometers, nanny-cam wavelengths, as I like to refer to them, they penetrate much deeper. And you can see much deeper into the skin. You're looking at, whereas here you see the spots on the skin due to the high melanin content and other types of colors in the skin. You can control the time of the photons. You could think of these photons, these are the Usain Bolt photons. They run really fast through the tissue. They don't probe quite as much volume. These photons, those are more the Albert photons. They take a little bit longer to get to the finish line. And they've taken a much more long path, but the idea is they're probing different depths based on their times of arrival. We'll talk about this in a little bit. Another way, again, of controlling photon path length and sampling volume is by controlling the space it probes. And in this case, we can just move a detector farther away, and you'll see in this highly cartoonized banana function, you can see that you're probing, again, different depths, different volumes of tissue, depending upon how far apart you put source and detector. So all of those are ways of controlling photon path length, and by changing the wavelength, the time, the space, you can actually recover absorption and scattering properties, which get you to all the good stuff that you saw earlier this morning. Okay? And just to remind you of a couple of numbers, in terms of characteristic values that you should remember, when we talk about space, the scattering path length, these are the individual scattering centers, you're looking at things on the order of 20 to 40 microns. Talking about cellular size or smaller. Lots and lots of scattering within the near-infrared wavelength region. In terms of time between collisions, you can see a very fast tenth of a picosecond or so. Really, really fast process of scattering. Whereas the key thing in the near-infrared is that the absorption path length and collision time, as you can see, is significantly longer. That means that if the photon only travels 1 millimeter in tissue, it's very hard to measure the absorption. Whereas you have to get very long path lengths if you want to accurately and reliably measure the absorption, at least in the near-infrared. Okay? I think Bruce put the same numbers up, but I'm just putting them up there because these are good numbers to have at parties. You can throw this stuff out and impress people. I do it all the time. It works. Anyway, a few other things I want to point out is that we're talking about this diffuse optical spectroscopy. I'm going to be referring mainly to deeper tissue penetration. You were treated beyond explanation about the wonders that Sylvain talked about with spatially resolved reflectance. Awesome, beautiful, we do it ourselves. I wish everyone could do that. However, we are going to be looking much deeper below the surface. We want to look at breast tumors, brain tissue. We've got to penetrate centimeters below the surface. So as I'll show, some of those techniques don't work as well when you have to go that deep. And since we're looking at things like brain, breast tumors, and muscle, we need a little extra giddy up on the photons in order to make it down there. Kind of like this dying laser pointer. So we'll use this one. Okay. Yeah, we'll deal with that later. Okay. Let's get into the nitty-gritty. Let's start looking at continuous wave intensity characteristics. Okay, so here's the classic problem. You have initial intensity I naught, you have some kind of homogeneous tissue. Yes, tissues are more complicated than that, but my simple mind only allows me to think of tissues as blocks of stuff. But with VP tools, you can do more. And we're going to use pretty classic near-infrared optical properties, absorption on the order of 0.01 inverse millimeters, and scattering, reduced scattering, of about 1 inverse millimeter. Noticing, again, the very high difference between those two values. So what exactly will the photons do when they enter this homogeneous slab of tissue? Well, as you know, one way that you can describe the propagation of photons in these media is to solve the Boltzmann transport equation. You don't want to do that, unless you really have to. And that's why people like Vasan and Jerry and Carol, they've done that work for you and given you things like this. So for example, you can make approximations to that very heinous equation, and you can realize that the photon propagation in many tissues follows a diffusive path. Very similar to heat moving down a rod, very similar to any kind of biological diffusive process you can imagine. Same type of equation. You see here that the gradient of if we look at the time rate change, in this case in the fluence, is mediated by the physical spreading of photons, in this case, not molecules. You lose photons due to absorption, right? You have molecules, hemoglobin, water, lipids. They remove those photons. They're gone forever. They don't come back. Roach Motel type stuff. And you're adding photons into the medium through a source, because some of these sources, like continuous wave, you're continuously adding photons. You're losing them through absorption, and the rest are spreading out in space and time. Now, if we're talking about, and I believe you kind of had a little bit of this already, in fact, much more detail than I have time to go into. But what I want you to realize is that if we just say, fine, let's not worry about time, let's just solve for this as a function of position from the source, we can solve for this and notice that the shape of this function is an exponential, a 1 over r exponential. That means that the intensity of light as you move farther away from the source is dropping very rapidly, and it's dropping in accordance with this effective attenuation coefficient, which I've defined in the bottom. The effective attenuation coefficient is a function of the absorption and scattering properties of your tissue. So what does that look like? Well, using VP tools, hopefully soon on Android phones, you never know. You're standing in line. You want to know what's going on, right? If we go back to this I naught with these optical properties, we can plot out the fluence distribution, I've done it in a log in this case, as a function of position inside of our two-dimensional tissue slab. And you will notice that, again, this is log, so you will see how rapidly this is dropping. This is about 30 millimeters below, 30 millimeters to either side. And you can see that by the time you get to the bottom, you have lost well over 6 orders of magnitude of signal. That's a lot of signal to lose. So what can we do? Well, we can make plots of how this looks. We can, for example, I kind of go over here. So if we put a detector, let's say 30 millimeters or somewhere on the surface, we put an optical fiber, let's say, we can calculate how is that fluence changing, or reflectance in this case on the surface, how is that reflectance changing with position? And you can see you get this very nice, the log of it, decay with respect, that's your spatially resolved reflectance signal. You can see the same thing more or less when you go in Z, when you go down inside of this tissue. You'll notice that it looks almost the same except for one key difference. That little blip there, by the way, is not an error. That little blip is because you'll notice, well, you can kind of see it here just in the graphic, but what's happening is that as the photons are injected into the tissue, you tend to get the largest back reflected signal about 1 transport mean free path below the surface. And that's where you get this increase, so to speak, in the fluence. And then, of course, as you go away from that, it's going to decay with that same 1 over r e to the minus r mu effective that you saw earlier. So we can calculate all of these things. And we can know, for example, that it's going to be difficult to get light to go 3 centimeters below the surface. So keeping that in mind, let's answer some important questions. What wavelength should we use if we want to go deep tissue penetration? We want to get to the brain, let's say. That's assuming you have a brain. I have proof I have a brain based on some of our experiments. What wavelength should I use if I want to go through the skull into, maybe I could use the visible. Well, let's find out using these tools. So what I've got here are a list of some very common wavelengths that are used in tissue spectroscopy with their corresponding absorption and scattering, reduced scattering properties. One is in the visible, 450 nanometers, a very lovely color. In this particular case, these are best guess optical properties from the literature. Scattering on the order of about 1.4. Absorption on the order of about 1.4. Scattering, comparable value. Near infrared wavelength, 750 nanometers. You can see significantly lower absorption and a scattering of about 1. And then we can go into more the shortwave infrared region where you can see the absorption goes way back up again, mostly due to things like water, and the scattering continues to decrease. So you can see that by these three wavelengths, we're looking effectively at three different regimes. You're looking at a scatter-dominated region. You're looking at also, well, maybe really two. I'm not looking at an absorption-dominated region. And you can see these two other regions are the absorption and scattering are comparable to one another, whereas in near-infrared, it's clearly not the case. So what do these things look like? Well, if we use the same thing, we plot out the fluence as a function of rho, that's the surface distance, and z, the depth, same image as before, with one key difference, the beauty of color bars. You will notice that whereas before the attenuation was 10 to the minus 6, you see now that this is 10 to the minus 60. Yeah. I looked this up because I was curious. I'd never heard of yoctowatts before, but that's basically what you would have. Another word you can impress your friends with at parties. So if you put 10 milliwatts in, that's what you get out. 10 to the minus 60 with respect to that. There is no known detector on this Earth that can see such a thing. I'm allowing for the case of aliens with better technologies than we have, but nevertheless, if I rescale this to match what we had before, in other words, let's say we lose 1 million times signal, you can see our penetration is significantly reduced. In other words, if I drew that line, I'm sorry, I forgot to mention that. Let's say that my brain is 15 millimeters below the surface. I have skull, I have skin. You can see that in the visible, you're just not going to get there. It's going to be way too hard. The absorption is too high. The scattering is too high. The light is just, it's exponential decay. It's not going to make it. This is why we don't do non-invasive brain sampling with 450 nanometer light. You can do skin. You can open up the brain, stick a probe on it, but you're not doing it through the skull. If you invent a detector to do that, come talk to me, but it's not happening. What if we go to the near-infrared? The near-infrared is kind of what I was doing before. You will see that as we get to that 15 millimeter band, you can see that, yeah, you lose about 3 to 4 orders of magnitude of signal. Possible. Putting 10 milliwatts in, you're getting down into the microwatts. That's, of course, you got to get the light to propagate back up into the detector. That's another story. And if we go to this swirl region, remember this one was much lower scattering, so you think you can penetrate much deeper, which is true, but the absorption is still quite high. You will see that again on that same scale, yeah, you can penetrate a little bit more, but again, you're going to run out of photons before you get down into the brain. So just by knowing optical properties, and by knowing diffusion models, delta P1 models, all those fun things you've been learning all week, and promptly, hopefully will never forget, you can actually predict the distribution of light inside of homogeneous tissues. Now, you can be more complicated and look at heterogeneous tissues, layered tissues. I'm not going to talk about that here. But the fact is that the physics of it is very similar. Just easier conceptually here. Okay? Any questions up to that point, just to make sure that we're all on the same wavelength? Any questions? Just making sure that I know it's Friday, you've been here all week, barbecue, you can smell it from BLI, so I don't want to. No. It depends on what you want to do. If you want to look at what's happening in my brain non-invasively, I would go with the 750. If you're doing a mouse, you could maybe do the 1200, although we have to obviously look at how much hemoglobin contrast you have at these wavelengths. But yeah, the near-infrared is used widely for cerebral oxygenation for a reason. Penetrates deeply, sensitivity to hemoglobin. Okay. Anything else? No? Okay, oh, sorry. All right, so this is all great, but I made this big sales pitch in the beginning, and I'm not even a salesman, about measuring absorption and scattering. So let's look into that with CW light. How can you use this information, these spatial distributions, to recover the optical properties of tissue, since this is where all the action is? Okay, so what we've done here is we've gone back to this model, and what I've got here is I'm plotting the reduced scattering versus the absorption for a variety of different optical properties, but I'm going to basically, you can see here that what did I do? Oh yeah, for different attenuation coefficients. So I'm picking various attenuation coefficients, and you can see that along these lines, you have the same mu effective. But you can see that because of this product, you can get different combinations of mu s prime and mu a that give the same effective attenuation. Let me just narrow in on one value, because I like the colors and everything. But I'm going to narrow in on this one value of 0.174 inverse millimeters, because that corresponds to many different optical properties, including 0.01 and 1 inverse millimeter, the very common ones that we used before. And you will see that there's a variety. This green line, hopefully that's showing up well. If not, I apologize. But you can see 0.01 and 1 is right about there. But you will see that there are many other combinations of optical properties that give the same effective attenuation. And this is exactly the problem. If your patient has an absorption of 0.03 versus 0.00001, you're going to come to very different clinical conclusions. In one case, they're dead. In the other case, they're bleeding. They've got a bruise in the brain. So it matters what this value is. So you saw before that you can use spatial resolved reflectance. You can measure, for example, a laser beam as a function of distance from the source. See how convenient this is? And I've plotted this out for you using, again, virtual photonics tools. You can plot out, I've normalized this signal just because it's easier, for 3 different cases. We're using the blue line, and I'll continue this theme throughout the rest of the lecture. The blue line is 0.01 and 1. The green line is higher absorption, 0.015, but a lower scattering, around 0.7. And the red line is lower absorption, 0.01, but a much higher scattering of 2. All of these have the same mu effective, but clearly very different scattering and absorption. And you can see that if I make this plot of the reflectance versus distance, you have a wide separation in the distance dependence of these signals. So you say, well, that's easy. The math shows it's clear that you can separate these out. There is, however, one small problem. You will notice that in this early distance, in the early distances, for several millimeters, is where you get the most contrast to separate scattering from absorption. And that is because at short path length, remember those characteristic lengths I told you about, the absorption path lengths are typically very long compared to scattering. So if the photon only travels 1, maybe 2 transport mean free paths, you're not giving it a lot of time to absorb, and your sensitivity to absorption will be low. Not only that, if I want to get to the brain, if I put a source and detector 3 millimeters away, good luck trying to penetrate into the brain. You won't be able to do it unless I drill a hole in my head, which I really don't want to do. So what we do instead is we say, fine, in the kind of world that I live in, we actually have to start from something like on the order of 10 millimeters. At that point, you get photon penetration several millimeters into tissue, which is still not enough for brain. But you can see now if I replot this data, but now I'm using 10 millimeters as my reference, you can see that now that difference in optical property sensitivity is starkly different. This is why in spatial resolved reflectance you have to measure both short distances and longer distances to maintain high separation of absorption and scattering. If you're only using far distances, as we do here, your sensitivity is strongly compromised. So for me to get to the brain, this method is very difficult to do. Now, one thing I want to say is I love spatial resolved reflectance. It's awesome, but as an experimentalist, I just want to point out a couple of issues with spatial resolved signals. For one thing is that those distances, you have to know, it's critical to know what those distances are. If they're wrong, then your distance dependence of the intensity is wrong and your optical properties are wrong. You have to be careful that whatever surface you're applying to, that you know how flat it is, because if the surface is curved, you're going to get a different intensity than if it's flat. That will show up as an optical property difference. That's why you saw the MI thing yesterday. That's why they do profiles to get the right surface shape to correct for that. The other thing is that if you're measuring intensity, no light source is perfectly stable. You have to correct for intensity fluctuations, because if the intensity goes down on your third measurement, let's say, it's going to look like an optical property change. So you can do this, but again, there are some experimental realities that you need to be aware of. Okay. So now, that's where I should have taken the break. Anyway, all right, so now that we've done that, let's see if we can do a little bit better, as great as spatial resolved is, let's see if we can do a little bit better by now improving this measurement by looking at the time dynamic characteristics of these same said photons. So we're going to now look at the time domain. Okay, so how does the time domain work? You've probably heard of something called LiDAR. It's used, for example, you will send a pulse at some target. The pulse takes a time to get to that target, reflect back to a detector, and then based on that distance, that time of flight, you can gauge the distance of the target, whether an airplane, a bird, somebody you're playing paintball with, or whatever it is. Time of flight tells you the distance away of whatever you're reflecting the light off of. Usually they use microwaves for that. But anyway, we're doing the same thing in the time domain, but with one key and very important difference. That is, when that pulse of light moves through a tissue, you fire a pulse, it doesn't just go straight through the tissue. We know that the pulse or the light will scatter. And as a result, that pulse undergoes tremendous dispersion as it moves through the sample, unlike LiDAR. And you can see an example of this. We have, for example, a pulse laser, something typically in the picosecond or better pulse width range. The shorter, the better. You might do some kind of filtering to get specific wavelengths you want. You fire this pulse, very sharp, narrow pulse of light, high energy density. You watch how that pulse evolves. You have a nice tight pulse, and as it moves through, it kind of spreads out in space and time. That was my attempt to be a picosecond pulse, moving more at seconds. But anyway. And you get this broadening, and that broadening is dependent upon the optical properties. If you have scattering and absorption, the evolution of that pulse, how it broadens, will change drastically. One other thing I'll mention is I like to live in the real world. I don't want to, but I have to. Is that, again, unless there's aliens on another planet that have such a detector, every detector has a delay response. There's no detector that works at billions of gigahertz or something like this, at least that I'm aware of. Maybe Apple has one, I don't know. But, or Hamamatsu. But nevertheless, all detectors have a little bit of a sluggish response, like when you wake up in the morning. When the photons hit the detector, they don't respond right away. There's a delay of some kind. And that's what you're seeing here. This over here, the red line, for example, or sorry, the blue line is, let's say, the physics of the light propagating through, it disperses out. But the red line is the detector response, meaning that when you hit a photon hits it, there's a lag time. What you're actually measuring is a convolution of these two processes. So as the photons are hitting, it's catching up to the photons that already hit it a few picoseconds earlier. It broadens out the signal, and it's actually an incredibly difficult thing to remove, as I'll explain in a moment. But I just want you to be aware of this before you get too high on any of these techniques. Okay. What about the physics, the modeling? Okay. If you go back to that time-dependent diffusion equation we had earlier, now you keep the t. This is the expression that you'll come up with. And let's just stare at how beautiful it is for a second. Gorgeous. This is what we had before. You'll see now that there is a similar field but different dependence on the optical properties. You'll see now that you have time throughout the function. You'll see that you get this r squared. Again, that's sort of like a, similar to what we saw before. But you'll see that there are these two different decay rates in the evolution of this time signal. One of them is going as the distance squared, the source detector separation. The other one is this long-term t. See, this one, of course, at long t is going to not be quite so strong. At longer t, this one will start to dominate. Almost like two competing effects, which actually wind up being scatter-dominated and absorption-dominated. We'll go over that in a second. But you can see, we want to see how this is going to change our measurement of optical properties. So what we've got here is we've got that same model I just showed you a second ago. Now we're using a source detector separation of 20 millimeters with these optical properties. We're not doing spatially resolved, right? But we could do that with time domain. I don't know why, but you could do it. And we can plot the intensity you detect with respect to time. Now notice the time scale. The time scale is nanoseconds. It's pretty fast. You'll see that you get this peak time, half a nanosecond or so after. This is assuming an ideal detector response. You can see that there's not much to the signal at early times. The reason for that is because there's a finite propagation time that it takes the photons to arrive. Very few photons will arrive unscattered at the detector, so we have very, very small signals. Again, this is a log plot, so you can see you're not going to get very much signal there. If you wait long enough, the onrush of photons come. This is the 405 at 4 o'clock, something like that for those who are Southern Californians, the freeway. And then after a while, you can see that this just decays off with time. Okay, that's great. How are we going to use this? Well, before we do that, let me just show you some other things. Is that the diffusion approximation is a very valuable thing to use, but it is not perfect in all cases. The diffusion approximation makes a critical assumption that the reduced scattering is much greater than the absorption of the tissue, or the sample, whatever you're measuring. And in many cases in the near-infrared, this is indeed the case. However, in other wavelength ranges, like the visible, that's not always true, as you saw earlier. So what we can do is we can actually use another VP tool. And sorry. Looks like our students are hard at work. That's good. It's not like I'm watching them or anything. It's just, just happens that way with Dropbox. Anyway, you can see that what happens here is that if we instead go to a Monte Carlo model, which does not make these assumptions anymore about the scattering has to be bigger than the absorption, all this kind of stuff. In principle, any optical property set will work, as long as you can get reflectance from it. And you will see that there is very good agreement between the models under these conditions. But what I want you to see, unless you have problems with color, which you might, you can see that at longer times, you can see that there's near perfect agreement between these. Hats off to VP yet again. But you will see that at shorter times, that the agreement is not quite as good. We can dive a little bit more into that. Whoops. Or not. Hold on a second. There we go. We can dive in a little bit more to that. I'm just blowing up this region of the curve here. And you can see that what's happening is that there is a kind of a time beyond which the process can be truly classified as diffusive. You need to have enough scattering events to efficiently randomize the photon direction. Once you have that, transport models and diffusive models agree very well. So in your modeling world, if you want to be truly accurate, you need to figure out if your system truly can be used, if you truly can use diffusive models or not. When we're doing breast tumors, for example, like Bruce showed you earlier, we're going centimeters below the surface. You won't get very much difference between Monte Carlo and diffusive models. On the other hand, if you're using smaller probes, where you're looking at shorter distances, let's say a couple of millimeters in a tissue or something like this, or you're working in different wavelength regions, this may no longer be true. And so you have to judge the accuracy of your model the choice of model based on how accurate it is for the optical properties that you want to measure. Okay. This is the same thing I was just showing before, but as an example, one of our students has developed, using the techniques that we've developed, a laparoscopic type probe, one that can be used at very short source detector separations. And you can see, for example, that if we compare at 5 millimeter source detector separation, pretty short for us, we're looking here at the time domain pulse between the diffusion model and this Monte Carlo model. And you can see for these optical properties, if you have very low scattering, you can see that the agreement is actually not that great. If you have tissues that have much higher scattering, in this case you can see the absorption is 0.01 and the scattering is 1.5, you can see that the agreement is excellent. Why is that? Even though it's a short distance, the higher scattering gives more time for those photons to randomize their direction. And as a result, the agreement between diffusion and Monte Carlo is better. The good news is that for this particular project, the scattering values for the tissue were actually about 1.5, and thus we could confidently use diffusion theory and didn't need the Monte Carlo model. Though in kidney, I'm not sure if that's true. But anyway, just for your consideration. Now, in terms of reality check, again, by experimental conditions, I mentioned before that in the time domain, I love the time domain. The time domain is awesome. But it's the high maintenance technique of the three, honestly. You know what I'm talking about, the kind of person that's a wonderful person, but they're just a lot of work to maintain. Time domain's like that. The calibration is very difficult because you have a time response that is a convolution of two products. That convolution process is incredibly difficult to unravel. In fact, we don't even do that. We actually take the model data and we convolve it with the instant response function and use that in the fitting. We don't try to deconvolve it and then fit. It's very difficult to do. Not only that, is that if you are doing what's called time-correlated single photon counting, which is the main advantage of time domain, you can count single photons moving through tissues. It's awesome. Except that it also picks up light from the monitor. It also picks up the person who turns on the room light. It picks up everything. So while it's very powerful, it's also incredibly sensitive, difficult to, when we do this, we have to watch out for every reflection off of every piece of optics in the lab, making it a little bit difficult to do in clinical situations, but it's fun nevertheless. Anyway, so time domain is awesome, but let me also go into reality space a little bit here, and that is that when I look at data, when I measure time domain curves, when you measure them, they never look like what I just showed up on the screen. And that is because these are predictive, these are analytic models, they're not taking into account noise. Using Monte Carlo methods, you can actually do that. This has been a very valuable tool for us. What we've done here is we have used the Monte Carlo tools to model, again, the time domain propagation using different numbers of photons. 2 million in blue all the way up to 50 million in purple. And in this case, it's the same optical properties we used before. Now you'll see that, of course, if I use 50 million photons, my time histogram is much larger. Again, I'm collecting more light. But let's look at what really matters in life. Besides love and all that great stuff, the other thing that matters is signal to noise, right? In that order. Love is more important, signal to noise is next important. Okay. If we replot this data in terms of signal to noise, you can see that the purple has much less variance in the signal than the blue. The blue was the 2 million, and the purple was the 50 million. And the point is that because with these transport-based models, Monte Carlo, it's not just doing a calculation, you're actually doing an experiment, a virtual experiment. And what's happening is you can see how the noise improves, or the signal-to-noise ratio improves, by adding more photons. You can use this, therefore, to design systems for how much throughput, how much efficiency do you need to have, how many photons per second do you need to collect. This is exactly what we use the VP tools for, among other things. That's kind of a nice feature bonus. Okay. So then to get back to the original point is, how do you exploit that temporal dependence to measure optical properties? Well, one thing that's really nice about the time domain is that you can actually depth section tissues depending upon their time of arrival. Unlike CW, where the photons are coming in, you're taking all comers. In the time domain, you can actually shift your detector to look at different windows of time. And here's an example of this. Let's say you put a source and detector at 25 millimeters apart, typical optical properties of tissues. Here's your impulse response, and here's your detected response. If you look at this time domain curve at different time points, you can see this window here of 200 picoseconds, let's say. What you're looking at is something a little bit more complex than what I showed before. This is not the fluence distribution of light, but rather it is something known as the photon PhD, the photon hitting density. And what you're looking at is the probability, the probability that light will reach a particular region of tissue and also be detected. So it's a kind of a product of two pieces of information. And what I really want you to glean from this, the most important thing, is that you will see that if you wait longer, you can see that your penetration depth into tissue changes. If I use the early photons, you see the penetration is shallower. If I use the later photons, the penetration is much deeper. And that's an important feature unique to the time domain. What about sensitivity to optical properties? Well, let's take a look again at different optical properties and their time domain curves. We're looking now at 3 different time domain curves for optical properties. In this particular case, the scattering is held constant, but the absorption changes. And what I want you to see is that each of these have different long-term slopes. Remember that equation we showed earlier? Right here, in fact. Oh, sorry, not right here. If you look at that time domain equation, and you take the natural, or you take the log of the reflectance and take the derivative of time, just to exploit some dependencies, you will see that what happens is the long-term behavior of these photons shows that you get almost a linear dependence on the absorption. And you will see that's exactly the case that you have here. If you wait long enough, the decay rate of photons with respect to time is a straight line, give or take noise in the system. And you will see that depending upon the optical properties, the absorption in this case, if I decrease the absorption, the slope is lower, and if I increase the absorption, the slope is steeper. Very high sensitivity to absorption in this particular case. What about scattering? Well, in this case, I'm now going to hold the absorption constant, 0.01 in every case, but we're going to change the scattering to 1 in blue, 1.25 in red, and 0.75 in green. And you will see that in this case, notice these lines are virtually parallel. Absorption is the same. Long-term evolution of those photons is the same. But you will see what's happening is that as the scattering increases, you will see the time of arrival is getting longer and longer. more collisions, takes longer for the photons to reach the detector. And most time domain detectors have, I mean, the worst ones I've seen, worst ones still more than you pay for your card, but nevertheless, you're looking at maybe 10 picosecond resolution. And you can see that that gives you plenty of resolution to resolve these particular time points. So notice now that if I go back to the original optical property set, same effective attenuation, but different combinations of absorption and scattering, you couldn't find 3 more different curves on the planet. You can see again that the time of arrival, if you look at the high scattering case, the green one is way off to the right, 1 nanosecond after launch. You can see that the high absorption case over here, the red one, has a very steep change. And then the green or the blue one is just the one we've been showing. So in other words, by measuring the time profile, you're effectively measuring the photon path length. And what you can do is you have very high sensitivity for separating different combinations of optical properties. And you can do this wherever you can collect light. One thing I'll mention, I won't have time to go into it, but I mentioned before that that's a beautiful story, except it's not that easy to deconvolve those signals. It's actually quite difficult. So one thing that's very a nice little thing that the time domain community has developed, something called the theory of moments, where what they do instead of measuring and then trying to deconvolve, what they do is they actually can calculate various moments of these time of flight distributions, and they can use them to recover optical properties. So for example, a moment is just defined as the time average of whatever signal you're talking about. The first moment, the K would be 1, the second moment it's 2, that kind of thing. And you can see that for some, using diffusion models, you can actually calculate the absorption and scattering properties based on these different moments. In this particular case, you can square it, or take the moment itself and square it. By doing different combinations of how the skewness and the time of flight and all that stuff, you can actually calculate this. The reason, you're saying, who cares? I can fit with MATLAB too. The reason you care about this is because you can do this devoid of having to deconvolve your data. You can actually calibrate your data by doing the convolution, or sorry, doing the moments with the convolved data. And you don't have to worry about trying to calibrate it. So this is why in the imaging community, this is virtually what everybody does, is they use these moments because they're much faster to calculate. They don't require knowledge of the incident response function. Okay. I mentioned this already, so I'm going to skip that. But let me just show you one more example. So something that we've been very interested in is how to recover optical properties from layered media. And one thing that I mentioned before is that we were talking about the long time behavior of those photons tends to mimic the, or it tends to be linear with respect to the absorption spectrum, right? Well, what if you have a layered system? What happens then? Well, in this particular case, this is a layered system designed to simulate a very thick top layer, in this case 12 millimeter top layer, and we've got basically a semi-infinite medium below with different optical properties. If you look at this time domain response, I want you to notice that what happens is that in the early time, the photons have mostly camped out in the top layer. And therefore, if you were trying to fit this, you would find optical properties that are mainly dependent upon the top layer. However, if you have a great detector and you wait longer and longer and longer, in this case, notice this time scale we're looking at, well, it's starting at 3 this time, but you're looking at 3 to 4 or 5 nanoseconds later, you can see what happens is that for photons that are mainly probing the top layer, you have this type of attenuation. Whereas when photons start to penetrate the bottom layer, you will see this shift in the time dependence of that signal that mainly reflects the bottom layer. And this is similar to what I mentioned earlier. By controlling the time of arrival, or not controlling, by measuring at different times of arrival, you can actually control how deep you're penetrating into your tissue and measure heterogeneous optical properties by using this time gating technique. It's the main reason I'm interested in the time domain. Okay. Let me just pause right there before we go into the frequency domain. Any questions up to this point? Yes?
Would you mind going back 2 slides? Well, I'm trying to actually go back 1 slide. I'm trying to reconcile what I'm seeing here with the previous 2 slides, where the different curves were parallel to each other as one property was held fixed and the other one's changing.
Right.
And I thought you might go from one curve down to the other, where here I'm not seeing the lines are parallel anymore.
Yeah, and the reason is because I kind of glossed over this. The top layer has a much higher absorption than the bottom layer. So this is a heterogeneous case. Those curves I showed earlier were all homogeneous cases. And so what's happening is that if I have shorter times, the probability that photons will reach the bottom layer is going to be lower. If I wait longer times, then the opposite is true, right? So the longer I wait, the more likely photons have actually probed the bottom layer. And then don't forget, they still have to propagate back up and get to the detector. And so that's the reason for this biphasic type curve, is that earlier photons are mainly being absorbed at the top layer and reflect that type of decay rate, whereas ones that also are probing the bottom layer have, in this case, since the absorption is lower, you can see that there is a leveling off of that curve because of the lower absorption. That's the reason. I pulled a fast one on you. It's a heterogeneous case.
Yeah, if in this case we hold the scattering is the larger one, right? 0.5 or 0.6?
Yeah, the scattering is similar between both layers in this particular case. It's a little higher in the bottom layer, but the optical properties are listed here. So it's about 0.5 in the top layer and about 0.65 in the bottom layer.
They're about the same. If you go back one slide, I was imagining that for the longer times in the signal you see, or back again, I was imagining we go from one parallel curve to another. Well, these aren't the parallel curves.
I'm sorry, you mean that one?
Yeah, and that's not what I'm seeing.
Well, yeah, and that's because the thing is, again, in this case, it's homogeneous. If it's heterogeneous, then since the transport is mainly dominated by scattering, still the scattering dynamics of the signal are still mainly reflective of the top layer. That layer model that I just showed you is actually very poor at measuring the bottom layer bottom layer scattering. You really need a two-layer model to do that accurately. So you sort of give up that information. If I had bigger contrast between the layers, it might be possible, but the idea is that, yes, this is also mediated a little bit by the scattering of the bottom layer, but at this point, the transport is mainly dominated by absorption more than the scattering. I don't know if that helps your...
Yeah,
does. Okay.
Yeah, thank you.
Very good. Was there another question, or did I answer it, or you just decided it's not important anymore? So, okay. One more.
I might miss this in your talk, so if you know the slope of those two curves, can you recover the optical properties?
You can, yes. And so you can do it one of two ways. One is that you can just look at, you can use these gating techniques, which is what we're doing. We use the gating techniques to only focus on this part of the curve, and we can recover the absorption based on that. If you really wanted to know the optical properties, that is the scattering as well, you would actually need to use a two-layer model, and you could fit different time portions to, for the two-layer model. That's a bit complicated to do at times. I mean, you can do it, of course, but we're trying to get real-time updates, and so we're trying to eliminate the need to do that. But yes, you can recover both layers if you have your instrument response function, and if you measure all these times, you could recover. In fact, people do this. They'll typically measure one or two different distances, maybe, in the time domain, and you can stratify the different layers based on their optical properties. Okay? All fun stuff. Okay. So let me just come up with the last leg of our discussion, and that is optical property measurement in the frequency domain. Now, earlier, you had heard about spatially resolved reflectance in both linear space and in frequency space. And you'll recall that when you're doing continuous wave measurements, as I showed earlier, you can look at, for example, the response, the intensity as a function of distance, or you can project patterns of intensity on your surface and project them with different frequencies. And so Von showed you that these are really just Fourier transforms of one another. Why should distance have all the fun? I don't know. Last time I checked, it was space-time, right? So time, you can do the exact same thing. In the time domain, as we just learned, you can fire a pulse, narrow bandwidth pulse, broadens in time, sensitive to optical properties. You can do the exact same thing in frequency space. In other words, the Fourier transform in time is the frequency domain, where instead of looking at the time evolution, you look at the response of the tissue to modulated signals at different frequencies, different temporal frequencies in this case. And there are advantages to doing that. I generally like the frequency domain, except for watches. I haven't found a good frequency domain watch yet. If you know one, Swatch maybe will make one, I don't know. That was a bad joke, I'm sorry. Anyway, it's lunchtime. Okay, how does the frequency domain work? What you do is you have, in our case, a sinusoidally modulated light source. So we're turning this light source on at high speed. I'll explain what speeds in a minute. You shine this into a tissue. So it's not a pulse, but it's oscillations. Stuff happens in the tissue, and you get a different signal coming back out. What do those signals look like? You can see this red curve is the excitation, and the way that we define the properties of this curve, there are three main parameters that we use. One of them is the average intensity. The average intensity is just known as the DC value, right? That's Dave Cuccia's initials, right? So that's just this dotted line over here. Then you have the amplitude of that. In other words, how much does this thing swing up and down? That's my initials, Albert Cerruti. That's why we get along so well, right? So you have your AC amplitude, your DC average. You also have one other parameter known as the phase shift. And you'll notice that this blue curve, which is the one that's been transmitted, in this case, through the tissue, you will see that there are changes to the AC amplitude, there are changes to the DC average, and also this curve is shifted in time. In the frequency domain, we don't think of it as time, we think of it as a phase shift. You can think of it as a lag. The scattering, which delays photons in time, also propagates a phase shift between the source and whatever's being detected, owing to the multiple scattering environment of these tissues. Now, a question arises, well, what frequencies do I need? I'm glad you asked. If you'll recall, we talked about scattering and absorption, path lengths, and all that. Here's just a loosey-goosey way of thinking about this. You can think of a time between collision. You can think of a space for collision. You can also think of a frequency of collision. If we convert our information into frequency space, in this case angular frequency, if we look at how fast, what frequencies is the individual scattering events occurring, they're occurring on timescales or frequencies well over 100 gigahertz. Yeah, once again, if you have a detector like that, let me know. But that's actually too fast. Anything over 100 gigahertz, you're modulating the signal without giving any time for the light to come back. You can't measure optical properties that way. In terms of transport frequencies, what type of frequency are we talking about? You're looking at things in the tens of gigahertz range. Quite fast. So to basically look at transport length scattering, what frequency is it occurring, we're not going to be able to sample faster than that frequency. We're going to be sampling much lower than that. But what I want to draw your attention to is the bottom line, that's the absorption. Remember, our goal is to separate absorption and scattering. And you will see that over the range of possible absorptions that we typically see in the near infrared, you can see that this frequency we're talking about is on the order of tens of megahertz to hundreds of megahertz. So that means that to measure absorption processes, that's the target range you want for your modulation frequencies. If you modulate much weaker than this, let's say 1 megahertz, you're letting the signal wake out too much, it's diffusing too much, you can't really separate the absorption and scattering. If you go wicked fast, it's kind of like me when I talk to people like, yeah, did you do this today? Did you get that? You're not even waiting for a response. It's too fast, it's too fast. I'm from New York, I'm very hyper with the 5 kids, I do this all the time. So anyway, I have to slow down. But what the point is that there's a sweet spot of frequencies that give you the best sensitivity to absorption, and that's going to be found in this tens to hundreds of megahertz range. So again, using modeling, it's great you do frequency domain, but unless you know where to look, you're going to get the wrong answer. You're not going to have any sensitivity. Okay. So how do we do this? Now that you know from theory, now that you know the rough idea about what frequencies, what temporal frequencies to use, what does the technology look like? Well, the main idea here is that you're using a source and you're going to be modulating it in some way. Now, there's many ways this has been done. By now, the most common way, the way that we do it, is actually by using laser diodes, that we can control the current to those laser diodes. That's what's shown over here. You can look at the optical power of these laser diodes with respect to the current you put in. You can pulse laser diodes. You can do a lot of great things, but modulating them is much easier. What we do is we send a current to turn them on, and then we oscillate a current to turn them on and off. All we do, an AC and a DC component. The power output of that laser diode, therefore, is modulated at a particular frequency. They're actually very robust at these frequencies. We shine that light through a tissue. As we're going to learn more mathematically in a second, the scattering and absorption processes will change the amplitude, the DC average, and the phase shift, or the timing of that light, with respect to the source. We take that signal and we can process it. There's many different ways to process it. There's homodyne, heterodyne, digital sampling, all that kind of stuff. But the idea is that we're looking for phase shifts and changes in amplitude of this diffusive wave moving through a tissue. And that's how we're going to calculate and measure optical properties. So Bruce, when he was, younger than me, I guess, a long time ago, he did something very clever. Actually, Bruce has done a lot of clever things, but this was perhaps one of his more clever moments. He's watching the time domain, and most of this is evolving, and people are showing this beautiful sensitivity. It's awesome, but the hardware was just too darn expensive. And Bruce said, well, I know from Fourier that the Fourier transform of the time domain is frequency space. So which frequency should I use in order to measure optical properties? And as Bruce usually says, he says all of them. I want all the frequencies, because that will give me the best sensitivity. Depends on the absorption. Remember, we showed that the range of absorptions you have, your ideal frequencies are anywhere from like 60 to 600 megahertz. So how do you know which one to pick? We don't discriminate. We measure them all. And so how we do that, and what Bruce came up with, his idea, was he used a network analyzer, which is a piece of test equipment, in order to modulate laser dyes. Now, we've since replaced those with hardware we've developed. But the idea is that the network analyzer was at the time an off-the-shelf answer to modulating light sources at high speed and doing it in swept fashion. And you can see an example of this. This is just a model of what it looks like. What we're doing is we send different frequencies, and you can see how that was played out. Isn't that pretty? Aren't you really impressed? I don't know, but anytime I make a video, I'm happy. The idea is you can see that we're sweeping through these frequencies, in this particular case, from 50 to 500 megahertz. Notice we're covering a lot of that range of optical property absorption values by changing the modulation characteristics of the laser diode, turning it on and off at 50 megahertz, then 51, 52, and all the way up to about 500. Depends on the application, but more or less that's what we do. And why you do that is because, again, the limit of the more frequencies you have, the more like you are to the time domain. Now, just like the time domain, there is a process by which the detector response will alter the signal that you detect. So you can see on the right, these are the signals that we, quote, recover, but these are more like the signals that we measure. How do you do that? Well, there's a process of calibration that we use. But one thing that's important is that if you recall, well, if you don't recall, you will after I say it. In the time domain, if you have a convolution, when you move to the frequency domain, what happens to that convolution? It becomes a product. And this is one of the biggest reasons people did the frequency domain. They realized that rather than deconvolving data, you could just do products instead. And that's one of the biggest reasons, by the way, that people do these well, not one of the biggest reasons, but it was a big reason that people adopted frequency domain methods in the past, because you don't have to do deconvolutions. So what do these signals look like? Well, lots of Greek letters. This is the extent of my ability to read Greek right here. But we can calculate, again, from diffusion theory, from the same formula that you saw earlier, but now in frequency space, not in time space. We can calculate, well, what is the amplitude and what is the phase shift of these detected signals? And I'll draw your attention to these heinous-looking functions. They're really a lot prettier than they look right now. But you can see that what you have is you have sensitivity, this little eta and these variables here. You will see that there's a wave vector, this k. This wave vector itself depends upon the optical properties. And what you're doing is you're measuring, in effect, this wave vector by looking at the phase and the amplitude. And then those, in turn, are functions of the optical properties. So let's get a little bit more intimate with what these things look like. So using those same equations available to you for free, might I add, on the Virtual Analytics website, you can plot out the amplitude of a photon density wave and the phase. And again, I'm using the same optical properties and distance I used earlier, 20 millimeters and 0.01 and 1. And let's take a look at these beautiful curves. I love them. You can see what happens is that as the frequency gets higher, you can see that the amplitude drops. And you can see that as the frequency gets higher, the phase shift increases. These are very typical characteristics. Now, again, this is the ideal case. This is not allowing for the fact that detector responses are frequency dependent and all of that. This is just what the theory predicts. And what you can see is that if you do a measurement at just one frequency, you have, let's say, an amplitude and a phase, you have absorption and scattering, there's a way to recover those optical properties. But if you have many frequencies, you can fit the entire curve and recover optical properties, absorption and scattering. Let's see what that looks like, because that's where all the fun is. Oh, one thing I should mention, by the way. Earlier we were talking about what frequencies do I use. What I want you to see, based on the theory, is why that's the case. Let's just say I look at the first few frequencies. This is the amplitude plotted for the first 100 megahertz. And I want you to see that the amplitude drop, in this particular case, is barely 1 to 2%. Most instruments have an error of at least 2 to 3% in their ability to measure amplitude. That means that if you define an FDPM system that measures at 40 megahertz or 20 megahertz, you better have basically infinite signal to noise if you want to measure changes in absorption. That's why people don't usually build systems at 1 megahertz or 10 megahertz. You have to increase the frequency to at least 50 megahertz to even be in the game. By the same virtue, if you look at the phase shift, you can see here, again, if you're only at a couple of let's say 10 megahertz or something like that, you can see you get a phase shift of maybe a couple of degrees. And again, many of these signals have an error of, let's say, anywhere from 0.1 to 0.5 degrees. If you're measuring a phase shift of 1 or 2 degrees with an error of 0.1 to 0.5, good luck trying to graduate with that. So anyway, that's another reason you just don't have enough phase shift with these small frequencies. The higher the frequency you generate, the bigger the phase shift. But then again, the experimental complexity goes up. But anyway, okay. Reality check, I was just going to mention this, is that, again, I love the frequency domain. It's awesome, but there are problems. For example, cell phones, guess what frequency range they work in? They work in a similar range, so you have to RF shield things, which is quite a pain. Sometimes to modulate light sources, they can be rather difficult. You have to have time-changing radio frequency signals, which can actually be tricky to deal with, but we have found solutions to this, by the way, I'm very excited about. Nevertheless, anyway, I get excited about this stuff. What can I say? All right, so to go back again to look at signal-to-noise analysis in the frequency domain, my data never looks like that. What would happen, again, if we use finite numbers of photons to calculate, in this case, phase and amplitude curves? Well, in this case, what we have is we're looking at the frequency response, again, for 2 million up to 50 million photons. And I'll draw your attention to the phase because it's a little easier to see. If we assume for a second that 50 million photons gives us the best phase noise, signal to noise, then what I want you to see is as you reduce the number of photons and you start looking at the phase error, I want you to see that as you have fewer and fewer photons, you get larger and larger error. That kind of just makes sense. If you have fewer photons, you're going to have more error. It's just a general fact of life. Noticing that the 2 million, you can see that your phase error could easily be a couple of degrees. And we talked before that if your phase shift was only several degrees and you have an error of a few degrees, you're out of luck. So again, you can do signal-to-noise analysis using these transport-based Monte Carlo methods and estimate what type of phase shift noise can I tolerate in order to make a measurement like this. It's a very useful thing, available for free. Okay, so then getting back to the theme, how do we use these tools? They don't pay me, by the way, to say that. How do we exploit the frequency domain to measure these optical properties? Okay. So what we've got here is we're going to look at now this fluence map, but now we're looking at it with respect to different modulation frequencies. I just want you to see this because it's kind of cool. But what happens as I change the modulation frequency, you will see what happens all on the same scale. You will see that the fluence distribution changes with respect to the modulation frequency I use. Remember, the DC, the zero frequency value, is looking at photons from all over. If I modulate at certain frequencies, we're keeping a certain time schedule. And you can see at 3 gigahertz, if you just look on the right, you can see that at the DC signal versus the AC 1 gigahertz signal, you can see that there are some small differences in the spatial distribution of that light. Generally speaking, using modulation frequencies from 0 to 500, it doesn't change all that much. If I play the video one more time, just because it took forever to make and I have to show it twice. I'm kidding. If you look, you can see that the scale for the first few hundred megahertz it doesn't change that much in this volume. But if you go to super high frequencies, let's say in the gigahertz range, notice what's happening is your probing volume is changing. It's the same idea as the time domain in that if you are measuring at shorter times, your probing tissues less in terms of their depth. Well, you can do the same thing in the frequency, although it's much more complicated to do here. Whoops. One more here. Okay, sorry about that. All right, so another thing that you can do, another way you can measure optical properties, I talked about many frequencies. I also want to mention you can also do it as a function of distance. And you can see here as an example, at this point we're looking at data at 850 nanometers. You'll notice that as a function of distance, you can change the phase shift or the amplitude. In this case, it's a log of the amplitude. You will see that these things change with respect to distance and to frequency. So if you make measurements of these phase and amplitudes at different distances and different frequencies, you can fairly reliably recover optical properties. I'll talk more about this in a second. I'm going to skip that for now. Okay, so let's go back to this because I can see it's lunchtime. Okay, let's now go to our case and we're going to plot out phases and amplitudes for different optical property sets, just like we did before. So first of all, the amplitude. Again, the standard optical property set of 0.01 and 1 in blue, higher absorption case, 0.015 in red, and the lower absorption case, 0.005 in green. You will see what happens as you change the absorption. The amplitude can go up or down. If I increase the absorption, the amplitude goes down. Kind of makes sense. But I want you to notice it doesn't just go down, but the frequency dependence goes down too. It changes. It's not just a bulk up and down. If I lower the absorption, again, I'm going to collect more photons, the amplitude goes up. If you want to see and target a little better the frequency dependence, we can plot something called the modulation. Well, what we do is we take the ratio of the AC value and divide it by the DC value, in other words, the zero frequency. And you can see that in the modulation plot, you can see that these three values have very different rates of decay with respect to their frequency. On the right, you can see what happens to the phase. In the phase, notice that, again, the blue is kind of our reference of 0.01 and 1. If I increase the absorption, in this particular case, you will see that the phase goes down. If I decrease the absorption, the phase goes up. Why is that? Basically, if I increase the absorption, the likelihood that photons will be deleted, longer path length photons, is going to be higher. The higher the absorption, the shorter the path length. If the photons travel shorter path lengths, the phase shift is lower. And that's the main reason for the phase dependence on the absorption. What about now changing the scattering? Same idea, of course, if I'm increasing, decreasing the scattering. In this case, the low scattering value is in green. The high scattering value is in red. Looking at the modulation, you'll see again that you get differences in the modulation. Notice that if I increase the scattering, the amplitude goes down. And if I increase the absorption, the amplitude goes down. And you say, well, wait, how are you going to tell the difference? I want you to look at the phase. Notice now what happens if I increase the scattering, notice the phase goes up. It goes up because you're increasing the path length more time the clock is running. If I kind of do this, make a video out of it, notice what happens. Higher absorption. Sorry, I was looking over here. Higher absorption, lower phase. Higher scattering, higher phase. You break the degeneracy with phase and amplitude between changes in absorption and scattering. That's why it's so cool. Besides the fact that, frequencies are awesome. Okay, then if I go back to our original thing where now we have all the different optical properties but the same effective attenuation, you can see again you have, just like the time domain, really wild differences in your phase and amplitude. You can see phases here of hundreds of degrees. That's actually quite easy to measure. I like those kind of signals. And you can see here for the low absorption, high scattering case, you have a demodulation that you might even be able to see, I don't know, maybe your iPhone can see that for crying out loud. That's a huge change. And these phase shifts are enormous. That again is owing to the variance in the optical properties, easily detectable with frequency domain techniques, just like the time domain. One other thing that has been developed over the years, I mentioned before about the distance dependence of these signals, is that one of the problems with frequency domain calibration when you do multi-frequency is that the light sources themselves change their behavior with different frequencies. There's capacitance in the light sources. Detectors have different frequency responses. So it's a little bit trickier to calibrate. So something that was developed in my former lab, Enrico's under his direction, was that you could actually recover the absorption and scattering properties of tissues by measuring the distance dependence of these frequency domain signals. And what was unique about this is you will see that you can derive from diffusion theory analytic expressions of mu a and mu s prime that are solely written in terms of the slopes of the phase and the AC intensity. There's no calibration terms in there. Now, there are still issues with this that you have to solve. For example, if you have multiple light sources, they have different intensities and whatnot. But this is actually the method that a company known as ISS uses, where they use multi-distance measurements in phantoms in tissues in order to recover the optical properties. Okay, so now, debating on what to do, since it's a little bit over already, I think we got a bit of a late start. Maybe I'll just kind of not bother with this part. What I was going to do was explain to you a little bit more about the technology that we have, but I can do that during the the demo. So we can talk a little bit more about that. But I'll just mention very briefly that one of the main problems that people have is a balance of information content and technological complexity. I'll just say it like this. So frequency and time domain methods are awesome, but you need pulsed or modulated light sources at every wavelength you want to measure. That can get rather expensive and cumbersome. CW, on the other hand, is much more easy to generate many colors of light, but again, not necessarily with, you can't modulate at hundreds of megahertz fluorescent lights. One of you could try, could be a fun project, but it's quite difficult to do. So what people have done, what we have done here in particular, is we found ways to combine, to do like the Reese's Pieces approach, to take frequency domain methods, which can measure absorption and scattering, and take continuous wave methods, which can measure a lot of wavelengths, and kludge them together so that you get the wavelength bandwidth of the broadband stuff, and you get the optical property separation from the frequency domain technique. You can do it in time domain as well if you wanted. And that gives you the best of both worlds. See, we don't bias ourselves with method over the other. We like them all. And so we do our best to be, the peacemakers of bringing these methods together to solve important biomedical problems. With that, I'm just going to summarize in the following way, and I'll talk more specifically about that technology as we have more time. So if I didn't bore you to death, which I hope is not, no one, you're all still alive. Okay, good. I'm just checking, because you never know. I talked about spatially resolved, I talked about time domain, I talked about frequency domain. In essence, all of these methods can separate and measure optical properties in tissues and tissue-like media. And you can do this by controlling the optical path length. You can control it by wavelength. Different wavelengths penetrate different depths in tissues, and you can see different features in the tissue. You can control it in space. You can do measurements at different distances or spatial frequencies and recover optical properties. You can also modulate in time, either with pulses or intensity modulation, and the propagation of those waves or patterns of light depend upon the optical properties. In order to accurately measure the molecular absorption of a tissue, and that's the good stuff. We want that information because that's got the hemoglobin, it's got the oxygen, hemoglobin oxygenation, it's got the water content. All that cool stuff you saw with Bruce doesn't work if you can't separate those signals. How do you do that? You control this path length in order to separate the effects of absorption and scattering, because the absorption and scattering occur at different length scales and time scales. When you probe different length scales and time scales, you can have sensitivity to those various dynamic processes. And ultimately, what that allows you to do is to calculate the molecular absorption concentrations and states of these absorbers, which is really what the whole clinical goal is in the first place. And then use that to detect cancer, look at brain response, whatever. And with that, I'll thank you for your time, your patience, and energy. And I guess I can answer some more questions, but since I guess the barbecue already started, may as well.